The first clue in the mystery of feather evolution came from the 150-million-year-old rock formations in Solenhofen, Germany. The thin, fine-grained limestone sheets open like the pages of a book written by nature long, long ago. One day in 1861, a page was turned that would unveil the most famous fossil in the world and a wonder of its age. Luis Chiappe, an expert on ancient birds, deciphers these pages of stone.
Well, Archaeopteryx was found in the middle of the 19th century, soon after Charles Darwin published his book on the origin of species. It was found in the midst of a huge controversy, the evolutionary debate, and it played such a critical role in turning this evolutionary debate to our understanding of how animals have transformed over time. It became an icon of evolution, some kind of paleontological Mona Lisa. So definitely the role of Archaeopteryx 150 years ago was that role of missing link, that role of intermediate between, on the one hand, animals that looked dinosaurian and animals that were birds, modern birds. What was critical at the time is that we have an animal with claws, an animal with teeth, an animal that looks very reptilian, but yet it has modern feathers.
Archaeopteryx was the first bird, but its feathers were already identical in shape and structure to those of living birds, so it tells us nothing about where feathers came from. That answer must be hidden in the ancestors of birds, fierce, meat-eating dinosaurs called theropods. You can look at the history of dinosaurs like a family tree. The first branch are the ornithischians, vegetarians like Triceratops and Stegosaurus. On the following branch are the sauropods, the giant long-necked dinosaurs like Apatosaurus, also known as Brachiosaurus. The closest relatives of these giants were the bipedal carnivores called the theropods, including Tyrannosaurus rex, Velociraptor, and birds. In the 1960s, John Ostrom of Yale University discovered another member of this nasty club, the raptor dinosaur Deinonychus. It played a critical role in proving the connection between birds and their theropod ancestors. Dinosaur biologist Jacques Gautier identifies the similarities between birds and this frightening theropod and demonstrates how its savage hunting habits may have laid the groundwork for flight.
Deinonychus changed us over from the conception of dinosaurs you see in the mural where dinosaurs are overgrown lizards to that these were active, cursorial, ran around for a living, very much more bird-like creatures, and that all stemmed from the description of Deinonychus antirophus. Well, you can just start with the head. Another obvious feature is rather than the teeth going underneath the orbit, it's just primitively the case in theropod dinosaurs, the entire tooth row is in front of the eyes. We're eventually going to make this into a beak. And you look at the forelimbs, you see these much longer arms. Dinosaurs start out with their forearms are only about half the length of their hind legs. Think of the Tyrannosaur up there with really diminutive little hands. As you get into these raptors within the theropods, they start getting these really long arms, as you can see here, that are nearly as long as the legs, with these gigantic mitt-like hands, a three-fingered hand that's fully a third the length of the entire arm. The old reconstructions, as you see here, showing kind of the limp bunny, wrist attitude. We've come to appreciate in recent years when we've gotten completely articulated hands, just like birds. All the motion takes place here in the wrist. They flick the hand fore and aft. And what this animal is doing is really playing praying mantis, in that it's holding its arms up folded against its body. The prey item doesn't think it's as close as it is, so to speak. So they have a stereotype motion where they go down and forward, grab their prey. up and back, down and forward, up and back. That's the flight stroke. That's exactly the way birds fly today. And we always wondered, well, how do you get power on the upstroke? They actually make this transformation in a muscle called the supracoracoideus that shoots the arm forward. And in birds, it actually lifts the arm up. But the motion made here is exactly the flight stroke. So these guys are grabbing prey items at considerable distance from their body. The prey item struggles in their grasp, and as a consequence, they stabilize the shoulder joint by fusing the two clavicles together to make a wishbone. And then they have to pull the prey back to them. There's power on the upstroke before you're flying. And so virtually all details of the flight stroke originate before flight. And that's the best part about the fossil record. There's no way you'd look at a flying bird today and go, obviously that forelimb came from a raptorial organ used to seize and secure prey. No way you would guess that. That's only the information you can get from the fossil record. These beasts were, ruling the day, and for 180 million years, dinosaurs were out in the daytime, and all the mammals are out at night. And the largest Mesozoic mammals, maybe the size of a possum or something. Most of them are mouse-sized. So we came out at night and stayed tiny for 180 million years. After the asteroid hit, knocked out at least the big dinosaurs, if not the little ones, the birds, but knocked out the big dinosaurs. That's the only time that mammals had the gumption to climb down out of trees and come out in the daytime. So we're lucky. We would not be here.
How did the arm motion of theropod dinosaurs evolve into the flight stroke of modern birds? To answer that question, Steve Gatesy is exploring just how birds use their bones, muscles, and feathers to fly.
What we're seeing here is a pigeon flying in a wind tunnel. This is the wind tunnel that Ken Dial from the University of Montana made, and he brought it to Harvard so that we could do a collaboration with Ferris Jenkins. And what we've done is taken the wind tunnel and put it in the X-ray facility so that we can take not only light video, as you see here, but also X-ray video, as you'll see in a minute. What the wind tunnel does is actually a big fan that creates an airstream through a plexiglass chamber that allows the bird to fly essentially in place. And so, although the bird seems to be stroking along rather slowly here, we've shot it with high-speed video, so it's actually flapping 6 times a second and flying at about 13 miles an hour. So what I've been doing is basically reconstructing that wind tunnel situation along with the cameras in this animation program in 3D. And so what we can do is take those videos and frame by frame paste them onto little cards essentially, so that if we're looking from the side, this is the picture we'd get from the side camera. If we're looking from above, here's the picture we'd see from above, and then that X-ray camera is going to stick in right on the side here. And by bringing in frame after frame, we've essentially then recreated from 3 different 2-dimensional views what was happening at any moment during that experiment in the wind tunnel. And so we're able to measure each of these motions. How is it moving up and down and forward and back? How is it pitching and rolling and yawing? And ultimately then, how are the wings responsible for producing those movements? And so how do they seem to pull off this amazing variety of things they can do? I think we've certainly gained an appreciation for just how complicated it is. How much they move, although it appears very stable to our eye. They're doing lots of small movements, compensating for a movement they might make during the downstroke, and then they'll undo it during the upstroke. Many of the people interested in flight are studying the outside of the bird, and rightly so. How the wings are moving, how those are producing the aerodynamic forces. Others are working sort of from the inside out. How are the muscles and the nerves creating the motors that are going to move this wing? At the same time, paleontologists are interested in skeletons and finding out how these fossils might have worked and how that relates to the origin of flight. And we'd like to think that the skeleton is really where all those intersect. And so a better knowledge of how the skeleton is moving in these living flying birds, I think, will really help all those fields. Not only for understanding how these joints work and how they might have worked in fossils, but for really understanding how the birds sort of pull it off.
Birds are the only animals that use feathers for powered flight. For over a century, the incredible adaptations of flight feathers would lead biologists to believe that feathers originally evolved for flight. But would this theory ever get off the ground?